Alrighty, so for this portion of the video, we are going to be discussing the heat diffusion equation in Cartesian coordinates in terms of finite differencing. So the first step in this derivation is remembering the equation that we derived in a previous video. So I've gone ahead and written that out here. So we have, we have three heat flow terms at the beginning of this equation. So we have the partial derivative with respect to a position in the x dimension of the quantity of the thermal conductivity K times the temperature gradient in the x direction. So that term is then repeated for y and z, and those are all added together. And then we also have Q dot, which represents the heat generation per unit volume inside our control volume. And then lastly, all of that added together equals our thermal energy storage term, which is equal to density of the material that we're working with times the specific heat capacity times the partial derivative of temperature with respect to time. So this is pretty complex. It's very general for any situation in the Cartesian coordinate system. But for this finite differencing derivation that we're going to do today, there's a few assumptions that we're going to make just to make the calculations a little bit easier. So the first assumption that we're going to make is that there is no heat generation at all within our system. So heat generation could come from a number of different sources, like a chemical reaction or some kind of artificial heating. However, for the sake of simplicity today, we're going to assume that that term is equal to 0. So I will go ahead and cross that out, and I'll also list our assumptions down here below. So our second assumption is that we're only going to be considering heat diffusion in the x direction. So instead of doing a problem in 3 dimensions, which is certainly possible, but very complex, we're only going to be considering the x direction for convenience. So I'll go ahead and cross these out as well. I'll write down that assumption. So our last assumption is that our thermal conductivity K is independent of position within the medium that we're dealing with. So that will just allow us to do some calculus rearrangements that will make our calculations a little bit easier. So I will list that one, and then we will proceed with the simplification. So I will list K is independent of position. Awesome. So with these three assumptions, this equation is going to be a lot more simple to work with and to use. So I'm going to go ahead and rewrite this down below, including these simplifications, and then we will go from there. So I'm going to begin by writing the partial derivative of temperature with respect to time. So it's going to be a partial big T over a partial small t. So dt over dt is going to be equal to alpha, which we'll define in just a minute, times the second derivative of temperature with respect to position. That's going to be partial squared t over partial x squared. So this is going to be our heat diffusion equation with these simplifications from these assumptions. So alpha, in this case, I'm going to circle that and write that out here. So in this case, alpha is going to be equal to K, our thermal conductivity, over rho Cp, where rho is the density of the material that we're working with, and Cp is that material's specific heat capacity. So alpha is equal to K over rho Cp. Now from here, I'll introduce the idea of finite differencing. So for this, for this demonstration, we're going to go ahead and talk about a bar, just a bar of some kind of material. I'll draw it here, and we're going to divide it into a few different chunks. Now, in a lot of problems like this, we divide it into infinitely small chunks like we have in past derivations. But the reason that this is called finite differencing is because we actually pick a finite amount of chunks that this is divided into. So just for the simple explanation and derivation today, I'll divide this bar into 4 different chunks. I'll number them 1, 2, 3, and 4. And I'll write bar underneath it, just so you remember that it's a bar. So in a problem like this, we could assume that the bar is being heated from one side over here. So I'll go ahead and write T infinity with some heat arrows going this way. Now, this is a simple case. Certainly, it could be being heated from one side or the other, or from many different directions, and we could certainly be doing this in other dimensions as well, not just x. But again, for the sake of simplicity, we'll just assume that our bar is only 4 chunks long. We're only dealing with heat coming in from one side. Very, very simple situation. So the way that we're going to approach this issue or this problem, we're going to rewrite our modified heat diffusion equation in terms of a notation that includes a T with a subscript J and a superscript N. So we're going to rewrite these derivatives in terms of this. So with this kind of notation, J is going to be our position index or our distance index. And N is going to be our time index. So J is going to refer to the position in the bar. N is going to refer to a position in time, so just an index that counts how far along we are from the beginning of the experiment. And T just represents the temperature at that specific instance, at that N, meaning when in time we're looking, and at that J, where in the bar we are looking. So again, T sub J and T superscript N. So we'll begin over here by rewriting our heat diffusion equation in Cartesian coordinates in the x direction with these modifications and these assumptions using this notation. So beginning on the left side, we have the derivative of temperature with respect to time. So we're going to rewrite this as T subscript J, because our position isn't changing here, only time, superscript N plus 1, because this is a certain time, one unit, one counting index in the future. We're going to go ahead and subtract T sub J superscript N, because this represents the same position, but an earlier moment in time. We're going to go ahead and divide that by the change in time. So this quantity here, I'll put this in brackets just to make it pretty clear. This is equivalent to dt temperature over dt for time. Next, we're just going to have our alpha, and I'm going to make some really big brackets because this side is going to be pretty large. So over here, we're going to represent the second derivative of temperature with respect to position using this same notation. Excuse me. So we will begin. And in this case, so over here, because position is being held constant, our J index, our position index didn't change, but our N did. In this case, our N position or our N index for time is going to stay the same. Also, I realized I just said index over here, not time index. So over on the right-hand side, because we're dealing with a derivative with respect to position, our N time index is going to stay the same, but our J position index is going to be the one that changes. So this expression over here, I made these brackets a little bit too large. This expression over here represents the second derivative of temperature with respect to position in the x direction, again, using the same T, J, N notation. Now, again, we can go ahead and do some more simplifications here. So I'm going to go ahead and rewrite this right side. I'll rewrite the left side as well. So again, on the left side, just as we had before, T sub j to the n minus 1 minus T sub j to the n over delta T. This is the first derivative of temperature with respect to time, equals our constant alpha, which again, just a reminder, is thermal conductivity over density times specific heat capacity. And then we can go ahead and combine these two terms and then combine our denominators as well. So I'll draw some more brackets, and we're going to have T j plus 1 to the n, and then we're going to have minus tjn. So we're going to have minus 2 t sub j to the n, and we're going to have minus plus, or minus minus, which is a plus, t sub j minus 1 to the n, all over x squared, because we can go ahead and combine these, because these two have the same denominator, and then it's all divided by delta x again, so divided by delta x squared. With some further simplifications, this equation is going to look something like this. So on the left-hand side, we're going to keep t sub j to the n plus 1 all by itself. And then over here, we're going to have t sub j to the n. And again, j is our position index, n is our time index. Plus, we can combine these three terms here and have alpha delta t over delta x, I'll use some parentheses there, delta x squared, times the quantity in brackets, this same set of t notation terms, so tj plus 1 and minus 2, tj to the n plus tj minus 1 to the n, close the bracket. So this is the finite differencing form of the heat diffusion equation in Cartesian coordinates. With these assumptions, we're only looking in the x direction, and there's no heat generation as well. So this is the form that we're going to use when we take this over to Python to model this on a computer. Now, when we actually do that modeling, this coefficient here, we're going to take this out and just call this r, lowercase r. And that's because these are all constants that are going to be given to us that aren't going to be considered as part of this equation. So again, this is the final form of the finite differencing form of the heat diffusion equation for Cartesian coordinates. And we will see you over in Python. All right, so we are going to hop into Colaboratory to perform a Python simulation of our finite differencing heat diffusion equation to simulate the temperature profile of a bar that is being uniformly heated from both ends at 350 and 400 Kelvin respectively. Now the bar itself is going to be at 300 Kelvin initially, and then it's going to be heated from both ends, so we're going to see that temperature profile develop. And again, this is using the finite differencing method of our heat diffusion equation. So to begin off our code, we're going to start by importing some things into our code. So the first thing we're going to do is import numpy as np. So this is going to allow us to perform some numerical calculations. And our calculation is actually going to be a vectorized calculation. So we're going to be working with matrices. So that's what numpy is going to allow us to do. So next one we're going to do is going to be set up some different tools for us to construct a plot. So we're going to do from plotly.subplots, import make underscore subplots. So again, this will allow us to construct our plot and see our temperature profiles as they evolve over time. Next one is going to be to import plotly.io as PO. And then finally, we're going to do PO.templates.default equal to plotly underscore dark. So these last two lines are just going to make our plot look a little bit prettier. So again, we're just importing some different tools that will allow us to continue on with our simulation. So we'll go ahead and do Shift Enter just to see if there are any errors that have been detected in this section of our code. Looks like we're going, we're loading, and we're good. So we're going to go ahead and proceed with the rest of our calculation. So with our finite differencing form of our heat diffusion equation for this problem, we're working with T sub j to the n notation. So that is the temperature at a specific location in space, j, and a specific moment in time, n. So j and n are our indexing values for both position in our medium. So in this case, it's going to be position in the bar. And then n is going to be that time index, so position in time or moment in time. So first thing we're going to do, we're going to define a variable as nx, and we're just going to say 100. So what this is saying is that we're going to have, doesn't need to be a period there, we're going to have 100 sections to our bar as we construct the model for this temperature profile. Next, we're going to do nt, which is just the number of time intervals that we're going to be analyzing this temperature profile over. So this could really be anything, but we're just going to do 10,000 as kind of an arbitrary large number. Next, we're going to define our R value. So in our equation for the finite differencing heat diffusion equation, we have R. So R is just we're using it as a single coefficient, but that represents alpha, which is a group of physical properties of our material, times delta T, divided by delta X squared, or quantity delta X squared. So we've got our number of physical chunks in our bar. We've got the number of time intervals over which we are analyzing, and we've got our R value as well. So next thing we're going to do is we're going to define the temperature of our bar initially. So the way that we're going to do this, we're going to build an array that has 100 units in it, and that they're all going to be 300, beginning at 300 Kelvin, because that's the initial condition of our bar in our problem. So we're going to go T equals NP, so numpy.full and then the number, the shape is going to be nx, so that's just going to be 100 values, and then their value is going to be 300 Kelvin, because again, that is given in our problem statement. Next, when we are graphing this, we're going to be graphing temperature in the y-axis and then position in our bar on the x-axis. So we also need to set up another array that's just going to serve as our x-axis. So we're going to do x as our array. Let's see, that's a lowercase x. It's going to be np.arrange, make sure I spell that right, and we're just going to have an x. So what that's going to do, again, is just set up an array of all of our values. So for 100 chunks of our bar, it's going to be integer values between 0 and 99, where the first one is 0, and the last one, the 100th value, is indexed as 99. So from here, there is one more step to initialize our bar and get it to its initial conditions. We're going to have to redefine the beginning and the final chunks in our bar. So that's going to be when j is equal to 0 and when j is equal to 99, respectively. So we're going to go ahead and do T0 is equal to 350 Kelvin. And again, this is just saying that we know our bar is 300 all the way across, but the chunk that's all the way on the left is going to be at 350 Kelvin instead of 300 Kelvin, because that is where the heat is going to be entering the bar, and that side of our bar is going to be held steady at 350 Kelvin. I have to do it for, oops, didn't mean to do that. Now we're going to have to do that for the other side as well. Now instead of going T99, we could do that, but then if we ever wanted to change our nx, we'd have to go in and do this manually. So we could also go T-1 and define that as 400 Kelvin. So again, instead of doing 99, we can do -1, which just takes us to the end of our array, to the end of our vector for the temperatures in our bar. And that's notation that's going to come in handy later on in our analysis as well. So we'll go ahead and do Shift-Enter for this section of code as well. Looks like we're ready to actually get into our figure, actually graphing this and going through that vector calculation for our temperature profile. So the first step is going to be defining our figure. So we're just going to go fig equals make subplots, which is that command that we brought in from plotly.subplots. And then we're going to have rows equal 1 and columns equal 1. So what that is saying is simply that we could make subplots. We could make like 10,000 different temperature profiles, but we're going to overlay them on top of each other. So we only need one row and one column in our graph, so just one figure, as it were. So let's see, our next line, we're going to go ahead and initialize that. We're going to go ahead and make our first plot on that graph. So that first one is just going to be 300 all the way across, and then up to 400 on one side and up to 350 on the other, or vice versa. 350 on the left and then 400 on the right. So we are going to do, let's see, we're going to do fig.add scatter. And then inside this, let's see, I might have done this wrong. Let's see, fig.add.scatter. You know what? We're just going to try it and see what it does. We're going to do fig.add underscore scatter. And so we're going to have x equals x, y equals t. Doesn't sound right. You know what? We're going to go with it. We're going to go with it and see what happens. So we've got x equals x, y equals t, and then next we're going to have name. We're going to have mode is equal to lines, and then finally we're going to have name is equal to initial. So this is just going to mark our first line on our graph, that first temperature profile with 300 all the way across and 350 on one side, and then 400 on the other side, and then 300 Kelvin all the way through the middle. So next we're going to have to set up a for loop, because we're going to have to do this several times and update our temperature profile as we go. So we're going to do for I in range. We're going to go from 1 to nt, and we're going to do nt plus 1 just so we do get that final unit of time in our 10,000 time unit range as well. So do that, and then now we actually are here for our calculation. So as you saw in the previous video when we were deriving the finite differencing form of our heat diffusion equation, it looks like T sub j to the n plus 1 equals T sub j to the n plus r times a bunch of stuff. So again, r is just that constant, all of those constants that are coming together, alpha times delta t over delta x squared. So the first term that we're going to have to define here is our initial starting temperature at some space j in our bar, some position j. So we're going to go ahead and do t, and then we're going to do 1, 2, -1. And those are going to be our indexing values for taking a slice of our overall array. So what this does, starting at 1 instead of 0, is going to exclude that first value, which we already know is at 450. We're not going to be doing any calculations there. That's at 450. That's set for the whole thing, always going to be there for the whole time period. And then we're just going to do that one more time, same thing. Oh, yes, and then going to -1 takes us all the way to the last one. But the way that the index works in Python, -1 is not going to be included. So in this case, the -1 value, as we defined earlier, will be 400, but that's not going to be included in this array. So we'll go ahead and do this one more time. It's the same exact thing. 1, :-1. All right, and then we're going to do plus r times, and then we're going to do open parentheses. So the way that this is going to work, our first value inside those parentheses, if we looked at the calculation or the equation that we derived in the last video, first one is going to be t sub j plus 1. So we're going to need to add 1 to these indexing values. So we're going to have t, and then open a bracket, and we're going to do 2, and that is going to be it. So we're going to do 2, starting at 1 space in, the next position in our bar, and then leaving that empty space there takes us all the way to the end of our, all the way to the end of our bar, all the way to the end of our array. And then we're going to do -2 times just the same temperature at the same spot one more time. So it's just going to be more t, and then open bracket 1, :-1. We're going to close that up, -1, close that up. And then we're going to add the previous temperature. So instead of adding 1 like we did, we're going to take 1 away. So we're going to do t, and then open those brackets, and we're going to have nothing at the beginning, and then take us to -2, which is going to be our second to last value all the way at the end of our array, so all the way at the end of our bar. Or the second from the end of our bar, that is. All right, so at this point, we're going to add in another command to check if our index I in our time interval, in the range of our time intervals, divides evenly into 100. Now that sounds a little bit abstract. What's going to look like if I %sign 100 equals 0. So what this is saying, the % is a modulus operator, which is just saying, does the index I divide evenly into 100? And if that is equal, it does, and then we're going to have it enter a print command, so to graph that temperature profile. If we didn't have this line of code in here, the program would go ahead and graph every single line, every single temperature profile, in fact, 10,000 of them on our graph. It would be really difficult to see what that pattern looks like. So this line just makes it so that it doesn't graph every single temperature profile, only graphs a few of them here and there. We can still see that trend, and it doesn't get too messy, but it still allows us to do 10,000 iterations of this temperature profile so that we can see how it develops over time. So inside of this if statement, this if command, we're going to just do another fig.add_scatter. And then we're going to do x equals x, y equals t, mode equals lines. And we're going to name each of those lines as well. But instead of naming them initial, we're just going to name them what the index actually is. So we're going to do f, and then open our single apostrophes, and then do braces I. So that's just going to allow us to print that, print that index on that line. So it doesn't say initial a bunch of times, it should just say this. So after this goes, you're going to go ahead and just go fig.show. It should show us our graph. So if we're all set, I'm going to go ahead and hit Shift Enter, and we will hope that it graphs something cool. Terrific. Okay, I thought that something in here looked a little bit funny, but I guess I did it correctly. But yeah, okay, so this is what our graph is going to look like with, again, 100 chunks of our bar, 10,000 units in times. We've done this 10,000 times. And if you notice, there aren't 10,000 lines on here. Our initial is this one down here, 300 all the way across, and then 400 all the way at the end. And then it only does multiples of 100, which are just the ones that divide evenly into 100, so we can actually see what's going on. But basically, we get this kind of banana shape, and we see at the beginning, it's 300 all the way across, and then as we go, we get to kind of a more of a curved line. We can see that temperature profile kind of developing, but it still looks a little bit swoopy, a little bit like a banana or a hammock. Those lines do get closer and closer and closer together as we go. And again, this is with an R value of 0.1. So let's go ahead and repeat this calculation, taking this up. We'll go 0.25 and see what it looks like. So we'll do Shift Enter and Shift Enter. So as we increase our R value, that R coefficient, we're approaching a line. It looks a lot more linear, still like a hammock, but definitely a lot tighter, or still like a banana, but more straight. We're getting a line that goes a little bit closer. It's still curvature, but it's still a little bit closer of a line between 350 and 400 at the left and right sides of our bar, respectively. Now, if we do this again, we're going to go to 0.5 and see what that looks like. Awesome. So that looks even better. So we've got almost a perfectly straight line. In fact, that probably is a perfectly straight line. I can't, from what I'm looking at right now, I can't tell that there's any curvature. So we've got a perfectly straight line between 350 and 400 degrees, or 400 Kelvin, that is. So let's go ahead and do 0.55 on our R value and do it one more time and see what happens. So this looks completely different. We don't see a straight line between 350 and 400 anymore. We see a lot of oscillation. We're seeing some very, very extreme values. Looks like we're in the neighborhood of 1 times 10 to the 298th. So very, very high numbers, super different graph. And this doesn't really give us any more information. So what we've demonstrated is that our finite differencing model for the heat diffusion equation is only stable at values of R equal to or less than 0.5. Now, this is a pretty serious limitation, because if we can only have our R be up to or between 0 and 0.5, that means that we can't have any really large intervals of time at delta t, because R is alpha times delta t divided by delta x. And we also can't have any really small delta x. We can't have any really small intervals in our bar. So we can get some cool graphs, but at any point where our R is greater than 0.5, we're getting a very unstable model here that isn't going to help us learn anything about our system or about the problem that we're trying to analyze. So we're going to walk through that stability analysis in the next step, and then we will go from there. Thank you.